Hello, welcome back. So we are still on the topic of angular velocity. I only have a couple of topics left. Um, and today we'll be talking about those and finally moving on to dynamics. So let me just quickly recap what we did last time. So we were looking at angular velocity and how it is related to the rate of change of different rotation parameters. We looked at rotation matrix, axis angle, and Euler parameters. So maybe I can just quickly show you what it was. So we saw R dot rotation matrix was minus this omega tilde, the skew symmetric matrix based on vector omega. So it was rotation matrix like that. For the axis angle, we had phi dot equals omega dot A and A dot, or the relative version of that. What you see when you are in the sitting with the rotating frame was 1/2 A cross omega minus cotangent of phi over 2 A cross omega. And this was axis angle rates, and for the Euler parameters, eta dot was minus 1/2 epsilon vector dot omega, and epsilon dot, again, this is epsilon. Epsilon dot, the relative version was 1/2, this is half, not z, 1/2 epsilon cross omega minus or plus 1/2 eta times omega. So honestly, rather complicated equations. But why are these useful? They are extremely useful in a very important way. And that is the equivalent of, so let me write it this way, that for instance, in a linear or translational motion, we had R dot was V. And from here, we could take integral, so find the position of a particle as the integral of v dt. So these equations I have on top are more or less equivalent of the same thing. So if I know my omega, know my angular velocity in a body frame, we have sensors for that, and in the equations we may be able to calculate these from other sources, such as the dynamics of the system. We can then take integral of any of these forms and no orientation, which is the equivalent of position, orientation in a space. So these are very useful for that particular application. But if you really think about it, for instance, the most visible one is axis angle, because it's the easiest to interpret. So you are in a space, you are rotating happily. It really doesn't matter, for instance, where you started from, what was the original frame that this A, for instance, comes from. You know you're rotating, and there is an axis in a space that you're rotating about at this particular instance, and you should be able to just easily calculate or know phi dot without worrying about where you were before, how much you have rotated so far. So Yeah, because of that, if we just focus at the current state and instantaneous changes of how the body is infinitesimally rotating about its current or from its current orientation, these equations can be a lot easier to interpret and understand and even argue for. So that's what we are trying to do. So we are only looking at a frame in a space in its current form, and just a tiny infinitesimal change in its orientation. So let me maybe write it down. Consider the frame XYZ and rotations. And let me write infinitesimal rotations to be infinitesimal rotations d theta x, d theta y, and d theta z about each of the x, y, and z axes. So these are very small rotations that are approaching zero. So a few things. First thing to note here is, well, how do I say this? So I want to describe this rotation for now. And the easiest way to start is by looking at rotation matrix. So if you remember rotation matrix about these principal axes have sines and cosines. But noting that sine of d theta is almost equal to d theta, and cosine of some d theta, where theta is a small, is approximately to 1. You can write your rotation. Let me move here. Or x rotation, let me call it drx. Just to show that it's a tiny rotation. It's not really a differential. drx is 1, 0, 0, 0, 0, cosine of d theta x, which is 1, sine of d theta x, which is d theta x, minus d theta x. Why am I writing so small? And 1 dry equals slightly bigger, so 0, 1, 0, 0, 0, cosine minus sine of d theta y. Do I have it right? Yes, this is minus d theta y and 1, and drz equals 0, 0, 1, 0, 0, cosine sine, which is d theta z, minus d theta z, and cosine. So I have these three rotation matrices. The interesting thing here to note that when you want to find the rotation matrix, the total rotation matrix after you have done all of these rotations, really doesn't matter in what sequence you try them, as long as there are infinitesimal rotations. So let's try drx, dry, drz. It is the same as dr, I don't know, x, drz, dry, or any other combination of them, or any other sequence, I would say. So they're all going to be the same and equal to 1 d theta z minus d theta y, d theta x, 1 d theta y, d theta o, no, d theta z, d theta y minus d theta x, and 1. And here you should note that it is true because any second differential, for instance, d theta, let me write it this way, d theta j is zero. Always these double differential. Whenever we in math and calculus, we have these double differentials. We tend to ignore those compared to single differential. So we treat them as zero. So with that assumption, all of these different sequences will end up with exactly the same rotation matrix. And it is the familiar form that we have seen many times. And this is, I'm gonna write it here, dr is I, the identity matrix, 3 by 3, minus d theta tilde. And this tilde, whenever we had, is that skew symmetric matrix that is 0 minus whatever z minus plus y and so on. So it is very easily, very nicely written in this form. So one thing, again, let me very explicitly mention it here. Sequence of infinitesimal rotations does not matter. And because of this, now it is possible for us to define something that we couldn't define before. So we can define a vector d theta. It's a vector. And it is d theta x along I plus d theta y along j plus d theta z along k. We couldn't do this before with finite rotations because order mattered. But now that order doesn't matter, I can define a rotation using right-hand rule with about an axis, for instance, I, j, and k. Each of those little axes can be considered as a each of those little rotations can be considered as a vector. With the right-hand rule, that's how you define the direction, and the magnitude is the angle of rotation, and you can essentially add them together and define this combined rotation vector d theta. So if you do this, let me see where I'm going with this. Now it is easy to think of angular velocity, omega, is d theta over dt, which is theta dot xi plus theta dot y along j plus theta dot along theta dot z along k. And this is my angular velocity that we had it before, but it is also nice to kind of look at it with almost the same but slightly different perspective where it came from. And from up there, when we define the rotation matrix, we can now see that our dot is really minus this tilde theta tilde dot, which is minus omega tilde. And this is the equation that we had before too. It is very similar, except that before we had some r pre-multiplied by r dot, but now that we are just looking at essentially one position, one orientation, that original rotation doesn't exist. It's identity matrix. So it is a simplified version of the same thing we had before. So that was rotation matrix. I have to go up. Another thing we have is axis angle. Axis and angle. So going back to the real definition of rotation about an axis. So this axis angle says if you have any kind of rotation, it is equivalent of rotating about a single axis by some angle. So what we have here is some axis A and some infinitesimal rotation about that axis phi. And this is equivalent to the summation of those d theta x, d theta y, d theta z. So these two rotations are the same. And kind of from the definition of now defining this rotation vector, d theta, it is the same, it follows exactly the same definitions as the axis angle. So it's a rotation about some axis with the amplitude or the magnitude of that vector being the amount of rotation. So this d phi times a, so axis of rotation is scaled by the magnitude of how much you're rotating, is my d theta. And from here, you can very easily see that because a is a unit, a norm of a is 1, a is unit vector. So d phi is actually norm of d theta, which equals this square root of d theta x squared plus d theta y squared plus d theta z squared. And you can quickly see this. And from again here, you can see a, the rotation axis is d theta x over d phi I plus d theta y d phi j plus d theta z d phi k. So if you know your tiny rotations about XYZ axis, you can very easily define the axis and angle of rotation. And going from this top equation that I had, d theta is d phi times a divided by a dt. So what you get is omega, which is d theta over dt. It equals d phi over, let me write it down, d phi over dt times a, which is phi dot times a. Let me try to box these. So this is a very nice compact form to think about angle and axis of rotation. If you're rotating with whatever angular velocity, your angular velocity is about that axis of rotation with the rate that you're rotating about that axis, so phi dot. And that can define your angular velocity vector. One other thing to note here, before we were talking about a dot, but here we at this instant that we are looking at a, we only define a. We cannot easily define a dot without considering how omega is changing. In other words, a dot in this view is dependent on the acceleration, angular acceleration, how omega is changing. Okay, that's that. And the last thing to talk about here, last but not least, is the Euler parameter. Euler parameters. And remember that we had epsilon. Epsilon vector was this axis of rotation scaled by the how much you have rotated. So essentially sine of phi over 2. This is not z, this is 2. In the differential form, we have this dE equals same a, but rotating about a with some infinitesimal rotation d phi. And sine of a small number is equal to that number, so a d phi over 2. And a d phi, I had it up there, a d phi is d theta. So it is 1/2 d theta, oh, not dot, d theta. So let me write it down here. dE equals d theta over 2. And you can take essentially divide it by dt, so E dot is theta dot over 2. What did I want to write? Yeah, okay, that's good enough. And theta dot is omega, so omega is 2 E dot or epsilon dot. So if you know how much you're rotating right now, your instantaneous value of Euler parameters, at least Ex, Ey, or epsilon x, epsilon y, and epsilon z, is just half of your angular velocity. And eta, which was eta, how do I write this? And eta is cosine of phi over 2, right? And when we have, let me think, my notation is strange. What is happening? So I'm not sure whether I should write d8 eta or just eta. Let me keep it as eta is cosine of d phi, but that doesn't make a lot of sense. And cosine of a small angle, let's go with this for now. I have to think. Equals 1. So eta is constant. But that can't be right. I have to think about this. Is it eta or d eta? If it is d eta, means eta, I don't know. Let me think about this. Anyways, all right, so I leave you with a question mark. That is it eta or d eta? Anyways, I don't know. So that's all I have for this video. So you can see if we just focus our attention in a infinitesimal rotation at the current instant, all of these axis angle and Euler parameters and rotation matrices, all of them take a simpler form and a lot easier to interpret and how they are changing. So, okay, that is all I have for now. In the next video, we cover one more topic on the angular velocity and we wrap this up. All right, until then.